So in this video, we're going to discuss how you can use natural logs to do some different things with exponential functions and how you can represent exponential functions in different ways. So before we begin, I want to make this note that if a equals e to the k, then k actually equals natural log of a. And that's because of this reason. If we have a equals e to the k, imagine if we were to do the natural log of each side, we had that property where almost essentially these like cancel out. And so the natural log of a equals k. And that's going to be important in a little bit. So there's two forms of exponential functions that are very common. The first one is what we call the annual or the period form, where we're discussing or we're representing what some future value is going to be at a specific or exact time period. Whereas in a continuous function, we're kind of looking at a similar idea, but here the difference is we're thinking of this thing as growing continuously. Alright, so if we're modeling growth, we've got A and K are actually the two things that are used to model growth. To determine if something's growing annually, we look at A, and if A is greater than 1, we have growth. And if A is between 0 and 1, we have decay. If we're looking at this continuous model, so I shouldn't say this is exponential, I should really say continuous. If K is greater than 0, it will be growth. If K is less than 0, we have decay. So the nice thing about a continuous function is it's very obvious what the growth or rate of decay is, but for an annual, we had previously discussed that. Remember, we need to uncover whatever R is. R represents our growth or decay rate. But for a continuous function, whatever K is the actual rate of growth. Okay, in this example, we want to convert P equals 150 e to the 0.08t into the annual or period form over here on the right. And so what I would say you want to note or notice is that we know P equals P naught e to the kt is the form for continuous, and P equals P naught a to the t is the form for annual. And what I would say you want to note is that these equations look very similar, except for e to the k is in place of a. That's really the only difference between these two. So looking at this equation, I know P naught, the initial value, is just whatever this front number is, which in this case is 150. So then e to the k is the same thing as a. So e to the 0.08 is the same thing as a. They're in the same position. And so we're going to use our TI-84 calculator, and you're going to need to look at the video below on how to actually evaluate that. But a comes out to be to 3 decimal places, 1.083. So now we have all the pieces that we need. We have a, and we have P naught. So P equals 150 times 1.083 to the t. That is our new function. That is the one we were trying to write. Okay, so we've got two forms now. We've got a continuous and we've got an annual. We are asked, what is the continuous growth rate? Well, we want to then consider the continuous model or the continuous function, this one here. And we said previously that whatever k is, whatever this value is, actually represents our rate. But that is in decimal form. Well, 0.08 in percentage form would be 8%. if we want to consider annual growth rate, we're going to look at our annual function or our period function that we created. P equals 150 times 1.083 to the t. And remember, this comes from R. Annual growth rate is determined by the R value, or this value here, 0.083, but we want to write that in decimal form. That would be 8.3%. So in the previous example, we went from a continuous model to an annual model. Here we're going to go the other direction. This says the gross world product is given by the function W equals 32.4 times 1.036 to the t. So notice this is really this form, W equals P naught A to the t. Because we just have a value, we don't have any E value in there. Where W is in trillions of dollars and T is the number of years since 2011. What is the annual growth rate of the gross world product? So here we're using the annual formula. We already have that. If it's W equals 32.4 times 1.036 to the t, the growth rate is the amount more than 1 when we're considering this A value. So I would say we really want to look at this 0.036. And we know that 0.036 in percentage form, that would be 3.6%. Now we're going to switch this annual model and turn it into continuous growth. We know the annual model would be this. In the continuous model, we're going to add in instead e to the kt. So notice A is in the same place as e to the k. So what we're trying to solve is if A is 1.036, we want that to equal e to the k. And as we previously discussed on the first slide, we would do this by using the natural log of each side. And what happens is that natural log cancels out e and we get k. K equals the natural log of 1.036. And using our calculator to evaluate that, k will equal 0.035. So we're trying to write this form, W equals P naught e to the kt. So W equals, our P naught, our initial value won't change from the first part, 32.4 E. The only thing that's new now is we have this KT part. I would say that's 0.035 to the T. And so the last question, then what is the continuous growth rate? The continuous growth rate corresponds to this number, the K number. But we want that number instead to be in percentage form, so I would say that's 3.5%.